Chapter 14 is cardiac output, blood flow, and blood pressure. So the cardiac output is the volume of blood pumped each minute by each ventricle. So cardiac output equals the stroke volume times the cardiac rate. So the average cardiac rate is about 70 beats per minute. The average stroke volume is 70 to 80 milliliters per beat, and the average cardiac output is about 5,500. So the regulation of cardiac rate. The spontaneous depolarization occurs at the SA node when the hyperpolarization activated cyclic nucleotide gated channels open, allowing sodium in. So the sympathetic norepinephrine and the adrenal epinephrine keep these channels open, increasing the heart rate. So the parasympathetic acetylcholine opens the potassium channels, slowing the heart rate, and it's controlled by the cardiac center of the medulla oblongata. The effect of the autonomic nerves on the pacemaker potentials in the SA node. The heart's rhythm is set by the rate of spontaneous depolarization in the SA node, and this depolarization is known as the pacemaker potential, and its rate is increased by the sympathetic nerve stimulation and decreased by the parasympathetic nerve inhibition. So the regulation of stroke volume, it's regulated by three variables. You have the end diastolic volume, EDV, the volume of blood in the ventricles at the end of the diastole, and it's sometimes called a preload, and the stroke volume increases with the increased end diastolic volume. You have the total peripheral resistance, so there's frictional resistance in the arteries, and inversely it's related to stroke volume. And then we have contractibility, so the strength of the ventricular contractions, so the stroke volume increases with contractibility. Okay, the Frank-Starling law and the sympathetic nerve effects. So the graph demonstrates the Frank-Starling law. As the end diastolic volume is increased, the stroke volume is increased. And the graph also demonstrates that by comparing the three curves, that the stroke volume is higher at any given end diastolic volume when the ventricle is stimulated by sympathetic nerves, and this is shown by the steeper curves to the left. See the red arrow. So the intrinsic control of contraction strength. Due to the myocardial stretch, the increased EDV stretches the myocardium, which increases contraction strength, and due to the increased myosin and actin overlap and increased sensitivity to calcium in the cardiac muscle cells. So the Frank-Starling law on the heart. When the heart muscle is subjected to an increasing degree of stretch, this is shown in A through D, it contracts more forcefully, and the contraction strength is indicated on the y-axis as the tension. And notice that the time required to reach each maximum contraction remains constant regardless of the degree of stretch. So the effect of muscle length and epinephrine on contraction strength. In this schematic comparison, all three curves demonstrate that each muscle contracts with its maximum force, so that's 100% relative tension at its own optimum length, 100% optimum length. So as the length is decreased from optimum, each curve demonstrates a decreased contraction strength. And notice that the decline is steeper for the cardiac muscle than for the skeletal muscle, and this demonstrates the importance of the Frank-Starling relationship in the heart physiology. So at any length, however, epinephrine increases the strength of myocardial contraction, demonstrating a positive inotropic effect. The venous return. So the end diastolic volume is controlled by factors that affect the venous return. So you have the total blood volume and you have the venous pressure. So the veins are compliant, which equals stretch at a given pressure, and they hold more blood than the arteries, but they maintain lower pressure. Okay, the venous return. So this is the distribution of blood within the circulatory system at rest. You can see the small veins, the large veins, the capillaries, systemic arteries, the heart, and the lungs. You notice that the venous system contains most of the blood. It functions as a reservoir for which more blood can be added to the circulatory under certain conditions such as exercise. Okay, factors in the venous return: the highest pressure in the venules versus the lowest pressure in the veins closest to the heart. So the sympathetic nerve activity to stimulate smooth muscles and lower compliance. These are all factors in venous return. There's also the skeletal muscle pumps and the pressure difference between the abdominal and the thoracic cavities and the blood volume. So the variable that affects the venous return and therefore the end diastolic volume, the direct relationships are indicated by solid arrows, and inverse relationships are shown with the dated arrows. Blood volume. So body water distribution. 2/3 of our body water is found in the cells, and of the remaining, 80% exists in the interstitial spaces and about 20% is in the blood plasma. So osmotic forces control the movement of water between the interstitial spaces and the capillaries, affecting blood volume. So urine formation and water intake, which is drinking, also play a role in blood volume. Okay, so on the left you see the intracellular. In the middle you have the interstitial fluid volume going back and forth, and on the right you have the blood plasma volume, and on the bottom you can see the water intake and the GI tract. Okay, so the distribution of body water between the intracellular and the extracellular compartments. The extracellular compartment includes that blood plasma and the interstitial tissue fluid. Tissue capillary fluid exchange. So the net filtration pressure is hydrostatic pressure of the blood in the capillaries minus the hydrostatic pressure of the fluid outside the capillaries. So the colloid osmotic pressure is due to the proteins dissolved in fluid, and the blood plasma has higher colloid osmotic pressure than the interstitial fluid. So this difference is called oncotic pressure, and it equals 25 millimeters of mercury. So this favors the movement of fluid into the capillaries. So the Starling forces, this is a combination of the hydrostatic pressure and the oncotic pressure that predicts the movement of fluid across the capillary membrane. So the fluid movement is proportional to fluid out minus fluid in, and this is the formula that we would use to figure that. So you have your hydrostatic pressure in the capillary, the colloid osmotic pressure of the interstitial fluid, and the hydrostatic pressure of the interstitial fluid, and the colloid osmotic pressure of the blood plasma. So these opposing forces affect fluid movement across the capillary. So the distribution of fluid across the wall of a capillary, the tissue or the interstitial fluid is formed by filtration, that's the yellow arrows, as a result of blood pressure at the arterial ends of the capillaries, and it is returned to the ventricular ends of the capillaries by the colloid osmotic pressure of the plasma proteins, and those are the orange arrows. Edema, this is excessive accumulation of interstitial fluids, and it might be the result of high arterial blood pressure, venous obstruction, leakage of plasma proteins into the interstitial space. It might be the excess production of mucin in the extracellular spaces caused by hypothyroidism, decreased plasma protein concentrations, or the obstruction of lymphatic drainage. So on the left, you can see some severe edema by elephantitis, which is a parasitic larva that blocks the lymphatic drainage that produces this tissue edema, and the tremendous enlargement of the limbs and the scrotum in this disease. Regulation of blood volume by the kidneys. So the formation of urine begins with filtration of fluid through the capillaries in the kidneys called glomeruli. So 180 liters of filtrate is moved across the glomeruli per day, yet only about 1.5 liters is actually removed as urine. The rest is reabsorbed into the blood, and the amount of fluid reabsorbed is controlled by several hormones in response to the body's needs. Antidiuretic hormone is produced by the hypothalamus and released when osmoreceptors there detect increased plasma osmolarity. So plasma osmolarity can increase due to excessive salt intake or dehydration. And increased plasma osmolarity also increases thirst. ADH stimulates water reabsorption in the body. So increased water intake and decreased urine formation increases blood volume. So blood becomes dilute and ADH is no longer released. Stretch receptors in the left atrium, carotid sinus, and aortic arch also inhibit the ADH release. So the negative feedback control of blood volume and blood osmolality. So thirst and ADH secretion, and it's triggered by the rise in plasma osmolality, and homeostasis is maintained by countermeasures including drinking and conservation of water by the kidneys. So aldosterone is secreted by the adrenal cortex indirectly when the blood volume and pressure are reduced. It stimulates reabsorption of salt in the kidneys, and it's regulated by the renin-angiotensin-aldosterone system. Okay, regulation of blood volume by kidneys, the renin-angiotensin-aldosterone system. So when the blood pressure is low, the cells in the kidneys secrete the enzyme renin, and angiotensin is converted to angiotensin 1, and angiotensin 1 is converted to angiotensin 2 by the ACE enzyme, which is the angiotensin converting enzyme. So the renin-angiotensin-aldosterone system. The system helps to maintain homeostasis through the negative feedback control of blood volume and pressure. So angiotensin 2 has many effects that result in a raise in blood pressure. There's vasoconstriction of the small arteries and the arterioles, and this stimulates the thirst center in the hypothalamus, and it stimulates the production of aldosterone in the adrenal cortex. The atrial natriuretic peptide is produced by the atria of the heart when stretch is detected. Excuse me. It promotes salt and water excretion in urine, and this is in response to increased blood flow, and it inhibits the ADH secretion. So this is the negative feedback correction of increased venous return. So the stimulation of stretch receptors in the left atrium causes secretion of the atrial natriuretic peptide, ANP, which increases urinary excretion of salt and water. And at the same time, stimulation of these stretch the receptor leads to decreased antidiuretic hormone, ADH secretion. And because ADH stimulates the kidneys to reabsorb and retain water, a fall in ADH works together with the increased ANP to increase the urine volume. So this maintains homeostasis by lowering the blood volume and the venous return. Vascular resistance to blood flow. So blood flow to the organs. Cardiac output is distributed unequally to different organs due to the unequal resistance to blood flow through the organs. Physical laws regulating the blood flow. Blood flows from a region of higher pressure to a region of lower pressure. So the rate of blood flow is proportional to the differences in pressure. So blood flow is produced by a pressure difference, and the flow of blood in the systemic circulation is ultimately dependent on the pressure difference between the mean pressure of about 100 millimeters of mercury at the origin of the flow in the aorta and the pressure at the end of the circuit, 0 millimeters of mercury in the vena cava, where it joins the right atrium. Okay, and the symbols on here, RA is the right atrium, RV is the right ventricle, LA is left atrium, and LV is left ventricle on this diagram. Okay, so the physical laws regulating blood flow. The rate of blood flow is also inversely proportional to the frictional resistance to blood flow within the vessels. So blood flow is equal to the pressure difference divided by the resistance at both ends of the tube. So resistance is measured as the length of the vessel times the viscosity of the blood divided by the radius of the blood vessel raised to the 4th power. So the relationships between blood flow, vessel radius, and the resistance. So the resistance and the blood flow are equally divided between the two branches of the vessels if we're looking at A on top. And on B, a doubling of the radius of one branch and having of the radius of the other produce a 16 increase in blood flow in the former and 16 decrease in blood flow in the latter. So a vessel length and blood viscosity do not vary normally, and the mean arterial pressure and vessel radius are therefore the most important factors in blood flow. Vasoconstriction of the arterioles provides the greatest resistance to blood flow and can redirect the flow to and from particular organs. So blood flow is increased by vasodilation. So blood pressure in different vessels of the systemic circulation. Notice that the pressure generated by the beating of the ventricle is largely dissipated by the time the blood gets into the venous system, and that this pressure drop occurs primarily as the blood goes through the arterioles and the capillaries. So the total peripheral resistance, the sum of all vascular resistance in the systemic circulation. So the blood flows to the organs and it runs parallel to each other. So a change in resistance within one organ does not affect another. And vasodilation in a large organ may decrease the total peripheral resistance and the mean arterial pressure. And increased cardiac output and vasodilation elsewhere make up for this. So the autonomic and the endocrine control of blood flow. Parasympathetic nerves. This increases the total peripheral resistance through the release of norepinephrine onto the smooth muscles of the arterioles in the viscera and the skin to stimulate vasoconstriction. And acetylcholine is released onto the skeletal muscles, resulting in increased vasodilation to these tissues, and this is due in part to the adrenal epinephrine. Okay, the parasympathetic nerves. You have acetylcholine that stimulates vasodilation. It's limited to the digestive tract, the external genitalia, and salivary glands. It's less important in controlling the total peripheral resistance due to the limited influence. So the paracrine control, the molecules produced by one tissue control another tissue within the same organ. So an example would be the tunica intima produces signals to influence smooth muscle activities in the tunica media. Smooth muscle relaxation is influenced by bradykinin, nitric oxide, and prostaglandin to produce vasodilation. So endothelin-1 stimulates the smooth muscle contraction to produce vasoconstriction and to raise the total peripheral resistance. Intrinsic regulation of blood flow. It's used by some organs, the brains and the kidneys, to promote the constant blood flow when there is fluctuation of blood pressure. It's also called autoregulation. Myogenic control mechanisms are the vascular smooth muscles that responds directly to changes in arterial blood pressure. Metabolic control mechanisms. Vasodilation is controlled by changes in the decreased oxygen concentrations due to increased metabolism, increased carbon dioxide concentrations, decreased tissue pH, and the release of potassium and paracrine signals. Okay, so next is blood flow to the heart and the skeletal muscles. Aerobic requirements of the heart. So the coronary arteries supply blood to a massive number of capillaries, 2,500 to 4,000 per cubic millimeter of tissue. So unlike most organs, blood flow is restricted during systole, so cardiac tissues therefore has myoglobin to store oxygen during diastole to be released in systole. So the cardiac tissue has lots of mitochondria and respiratory enzymes, so it is metabolically very active. So during exercise, the coronary arteries increase blood flow from 80 milliliters to 400 milliliters per minute per 100 grams of tissue. So regulation of the coronary blood flow. Norepinephrine from the sympathetic nerve fibers stimulates vasoconstriction, raising the vascular resistance at rest, and the adrenal epinephrine stimulates vasodilation and therefore vascular resistance during exercise. So vasodilation is enhanced by intrinsic metabolic control mechanisms. So the regulation of blood flow through the skeletal muscles. The arterioles have high vascular resistance at rest, so even at rest, skeletal muscles still receive 20 to 25% of the body's blood supply. Vasodilation is stimulated by both adrenal epinephrine and sympathetic acetylcholine. Intrinsic metabolic controls enhance vasodilation during exercise. So vascular resistance to skeletal and cardiac muscles decreases during exercise due to an increased cardiac output, metabolic vasodilation, and the diversion of blood away from the viscera and the skin. So blood flow to the brain increases a small amount with moderate exercise, and it decreases a small amount during intense exercise. So cardiac output can increase 5 times due to the increased cardiac rate, and the stroke volume can increase some due to the increased venous return. So blood flow to the brain and the skin. So cerebral circulation. The brain cannot tolerate much variation in blood flow. So unless the mean arterial pressure becomes very high, there is little sympathetic control of blood flow to the brain. So at high pressure, vasoconstriction occurs to protect the small vessels from damage and stroke. So when the blood pressure falls, the cerebral vessels automatically dilate, and when the blood pressure rises, cerebral vessels automatically constrict. So decreased pH of the cerebral spinal fluid, or the buildup of CO2, also causes arterial dilation. The most active regions of the brain must receive increased blood flow due to arterial sensitivity to metabolic changes. So astrocytes may play a role in this. So cutaneous blood flow. The skin can tolerate the greatest fluctuations in blood flow. The skin helps control body temperature in a changing environment by regulating blood flow, and this equals thermoregulation. So increased blood flow to the capillaries in the skin releases heat when the body temperature increases. Sweat is also produced to aid in heat loss. Bradykinins in the sweat glands also stimulate vasodilation in the skin. Vasoconstriction of the arterioles keeps heat in the body when the ambient temperatures are low. So this is aided by the arteriovenous anastomoses, which shunt blood from the arterioles directly to the venules. So cold temperatures activate the sympathetic vasoconstriction, and this is tolerated due to decreased metabolic activity in the skin. So at the average ambient temperatures, the vascular resistance in the skin is high and the blood flow is low. So the sympathetic stimulation reduces the blood flow further. And with continuous exercise, the need to regulate the body temperature overloads and the vasodilation occurs. This may result in lowered total peripheral resistance if not for the increased cardiac output. But if a person exercises in very hot weather, he or she may experience extreme drops in blood pressure after reduced cardiac output. So this condition can be very dangerous. So the circulation in the skin showing the arteriovenous anastomosis. The vessels function as shunts, allowing blood to be diverted directly from the arteriole to the venule and to bypass the superficial capillary loops. Blood pressure. So the blood pressure is affected by blood volume over stroke volume, total peripheral resistance, and cardiac rate. So an increase in any of these will increase the blood pressure. Vasoconstriction of the arterioles raise the blood pressure upstream in the arteries. So the effect of vasoconstriction on blood pressure, a constriction increases blood pressure upstream. This is analogous to the arterial pressure, and it decreases pressure downstream. This is analogous to the capillary and the venous pressure. And the capillary blood pressure is low because of a large total cross-sectional area that you can see here in the middle. So the kidneys can control blood volume and therefore stroke volume. And the sympathoadrenal system stimulates vasoconstriction of the arterioles, raising the total peripheral resistance and the increased cardiac output. Baroreceptor reflex is activated by changes in blood pressure detected by the baroreceptors in the aortic arch in the carotid sinuses. So increased blood pressure stretches these receptors, increasing action potentials to the vasomotor and the cardiac control centers in the medulla. It's most sensitive to drops in blood pressure. So the effect of blood pressure on the baroreceptors response. This is a recording of the action potential frequencies in sensory nerve fibers from the baroreceptors in the carotid sinus and the aortic arch. So as the blood pressure increases, the baroreceptors become increasingly stretched, and this results in a higher frequency of action potentials transmitted to the cardiac and the vasomotor control centers in the medulla oblongata. So the vasomotor center controls the vasodilation and constriction, and the cardiac center controls the heart rate. Okay, so the structures involved in the baroreceptor reflex. The sensory stimuli from the baroreceptors in the carotid sinus and the aortic arch, acting via control centers in the medulla oblongata. These affect the activity of the sympathetic and the parasympathetic nerve fibers in the heart. So a fall in blood pressure equals an increase in sympathetic and a decrease in the parasympathetic activity. So this results in increased heart rate and total peripheral resistance. A rise in blood pressure has the opposite effects. It's good for a quick beat-by-beat regulation. Okay, so the negative feedback control blood pressure by the baroreceptor reflex. This reflex helps to maintain an adequate blood pressure upon standing. Sorry. Atrial stretch reflexes. So these are activated by increased venous return to stimulate the tachycardia, inhibit the ADH release, which results in the excretion of more urine, and to stimulate the secretion of atrial natriuretic peptide that results in the excretion of more salts and water in the urine. Hypertension, shock, and congestive heart failure. So hypertension is high blood pressure, and 20% of Americans have hypertension. It can increase the risk of cardiac diseases and stroke, and it can be classified as essential or secondary. So secondary hypertension is a symptom of another disease, such as kidney disease. Essential hypertension. Most people fall in this category, so the cause is difficult to determine, and it may involve any of the following. It can be increased salt intake coupled with decreased kidney filtering ability, increased sympathetic nerve activity, increasing the heart rate, or responses to the paracrine regulators from the endothelium. So the dangers of hypertension, vascular damage within the organs, especially dangerous in the cerebral vessels, leading to stroke, ventricular overload to eject blood, leading to arrhythmias and cardiac arrest, and it contributes to the development of atherosclerosis. So the treatments for hypertension, lifestyle modification. First of all, you limit your salt intake, you limit smoking and drinking, you lose weight, and you exercise. Potassium and possibly calcium supplements, diuretics to increase urine formation, beta blockers to decrease cardiac rate, and ACE inhibitors to block angiotensin II production. Circulatory shock. So this occurs when there is inadequate blood flow to match the oxygen usage in the tissues. Systems result from inadequate blood flow and how our circulatory system changes to compensate, and sometimes shock can lead to death. So hypovolemic shock, this is due to low blood volume from an injury, dehydration, or burns, and it's characterized by decreased cardiac output and blood pressure. Blood is diverted to the heart and the brain at the expense of other organs. Compensation includes baroreceptor reflex, which lowers the blood pressure, raises the heart rate, which raises the peripheral resistance, and it produces cold, clammy skin and low urine output. So septic shock. This is a dangerously low blood pressure due to an infection, sepsis. Bacterial toxin induce nitric oxide production, causing widespread vasodilation. The mortality rate is high, 50 to 70%. Severe allergic reactions can cause anaphylactic shock due to the production of histamine and resulting vasodilation. Spinal cord injury or anesthesis can cause neurogenic shock due to the loss of sympathetic stimulation, and cardiac failure can cause cardiogenic shock. Congestive heart failure. This occurs when the cardiac output is not sufficient to maintain blood flow required by the body. It's caused by myocardial infarction, congenital defects, hypertension, aortic valve stenosis, or disturbances in the electrolyte levels of potassium and calcium. It's similar to the hypovolemic shock in symptoms.